Hello student, welcome in Department of Nanoscience and Nanotechnology S.Y.B.Sc class. Today's lecture is based on spectroscopic techniques, that is AAS, X-ray fluorescence and Sem EDS spectroscopic techniques. So first of all, what is AAS? Means atomic absorption spectroscopy. Atomic absorption spectroscopy uses the absorption of light to measure the concentration of gas phase atoms. Since samples are usually liquids or solids, the analyte atoms or ions must be vaporized in a flame or graphite furnace. The atoms absorb ultraviolet or visible light and make transitions to higher electronic energy. The analyte concentration is determined from the amount of absorption. Applying the Beer-Lambert's law directly in AA spectroscopy is difficult due to variations in the atomization efficiency from the sample matrix and non-uniformity of concentration and path length of analyte atoms. Concentration measurements are usually determined from a working curve after calibrating the instrument with standards of known concentration. Next, construction and working of AS system. This is the schematic of atomic absorption experiment. The instrument contains source, that is hollow cathode lamp, lenses, atomized samples, monochromator, detector, amplifier and readout. So, first is light source. The light source is usually a hollow cathode lamp of the element that is being measured. Lasers are also used in research instruments since lasers are intense enough to excite atoms to higher energy levels. They allow AA and atomic fluorescence measurement in a single instrument. The disadvantage of these narrow band light sources is that only one element is measurable at a time. Next is atomizer. AA spectroscopy requires that the analyte atoms be in the gas phase. Ions or atoms in a sample must be undergo desolation and vaporization in a high temperature source such as a flame or graphite furnace. Flame AA can only analyze solutions while graphite furnace AA can accept solutions, slurries or solid samples. Flame AA uses a slot type burner to increase the path length and therefore to increase the total absorbance. Sample solutions are usually aspirated with the gas flow into a nebulizing or mixing chamber to form small droplets before entering the flame. The graphite furnace has several advantages over a flame. It is a much more efficient atomizer than a flame and it can directly accept very small absolute quantities of sample. It also provides a reducing environment for easily oxidized elements. Samples are placed directly in the graphite furnace and the furnace is electrically heated in several steps to dry the sample, ash organic matter and vaporize the analyte atoms. Then light separation. AA spectrometers use monochromators and detectors for UV and visible light. The main purpose of the monochromator is to isolate the absorption line from background light due to interferences. Simple dedicated AA instruments often replace the monochromator with a band pass interference filter. Photomultiplier tubes are the most common detectors for AA spectroscopy. Next is applications. There are many applications for atomic absorption. First is clinical analysis, analyzing metals in biological fluids such as blood and urine. Second is environmental analysis, monitoring our environment. For example, finding out the levels of various elements in rivers, seawater, drinking water, air and petrol. Third one is pharmaceuticals. In some pharmaceutical manufacturing processes, minute quantities of a catalyst used in the process, usually a metal, are sometimes present in the final product. By using AAS, the amount of catalyst present can be determined. Fourth one is industry. Many raw materials are examined and AS is widely used to check that the major elements are present and that toxic impurities are lower than specified. For example, in concrete, where calcium is a major constituent, the lead level should be low because it is toxic. Next spectroscopic method is X-ray fluorescence spectroscopy, that is XRF. The energy dispersive X-ray fluorescence spectroscopy is a method for measuring the thickness of coatings and for analyzing materials. It can be used for the qualitative and quantitative determination of the elemental composition of a material sample as well as for measuring coatings and coating systems. In both laboratory and industrial environments, the fluorescence spectroscopy is now well established and can be readily utilized with modern equipment. XRF instruments have the following advantages. First is non-destructive. The X radiation has absolutely no lasting influence on the material. It fully retains its quality. Next is fast. The XRF method needs very simple sample preparation and short measurement times range in the seconds, rarely longer than 1 minute. Next is clean. No chemicals are used. Next advantage of XRF is safe. Method without the use of environmentally hazardous chemicals. X radiation poses no risk for operator due to the protective instrument design. Next is universally applicable. The XRF method is suitable for material analysis and coating thickness measurement in a very broad range of applications. Principle of XRF spectroscopy. The diagram shows the principle of XRF spectroscopy. That is, the specimen is excited with the primary X radiation. In the process, electrons from the inner electron shells are knocked. Electrons from outer electron shells fill the resultant voids, emitting a fluorescence radiation that is characteristic in its energy distribution for a particular material. This fluorescence radiation is evaluated by the detector. The generation of the X-ray fluorescent radiation is shown simplified in the figure. One electron from the K shell is knocked. The resultant void is filled by either an electron from the L shell or an electron from the M shell. In the process, the K alpha and K beta radiation is generated, which is characteristic for the particular material. Next is functional principle of X-ray fluorescence spectroscopy instrument. The diagram shows the functional principle of XRF. The X-ray tube generates the primary X radiation. The electrically heated cathode emit electrons. Accelerated by the applied high voltage to very high speeds, the electrons bombard the anode material. This generates the primary X radiation. The shutter serves as a safety device and closes the access of the primary X radiation to the measurement chamber if needed. A light source, which is not shown in figure, a light source illuminates the sample. A mirror and lens direct the image of the measurement location to a color video camera. The mirror has a hole in its center for the primary radiation to pass through. The aperture or collimator limits the cross-section of the primary beam in order to excite a measurement spot of a defined size. The primary X radiation impacts the atoms on the sample surface, that is coating layer and base material, and in the process knocks electrons from the inner electron shell. Electrons from outer electron shells fill the resultant voids, emitting a fluorescence radiation that is characteristic in its energy distribution for particular material. The energy dispersive detector measures the energy distribution of the fluorescence radiation. A multistage electronic circuit processes the measurement signals. The measured spectrum shows lines or peaks that are characteristic for the chemical elements in the sample. The instrument computes the thickness of the coatings and the analysis result. So this is X-ray fluorescence spectroscopy. Now we will see the same EDS, that is secondary electron microscopy with energy dispersive X-ray analysis. First of all, principle of SEM EDS. SEM is essentially a high magnification microscope which uses a focused scan electron beam to produce image of the sample, both top down and with the necessary sample preparation cross sections. The primary electron beam interacts with the sample in a number of key ways. First is primary electrons generate low energy secondary electrons which tend to emphasize the topographic nature of the specimen. Primary electrons can be backscattered which produces images with a high degree of atomic number Z contrast. Ionized atoms can relax by electron shell to shell transitions which lead to either X-ray emission or Auger electron ejection. The X-ray emitted are characteristic of the elements in the top few micrometer of the sample and are measured by the EDS detector. Next is EDS analysis with SEM. From searching for good contaminants to identifying machine malfunctions to predicting how an aircraft part will corrode over time. Energy dispersive X-ray analysis is a widely employed technique by today's material science and used together with a scanning electron microscope. EDX detector can generate more information about a sample than SEM can alone. Using EDX, researchers can quickly generate information about the chemical composition of a sample, including what elements are present as well as their distribution and concentration. But how exactly does EDX work? With SEM, a variety of signals offer up different information about a given sample. For example, backscattered electrons produce images with contrast that carry information about the differences in the atomic number, while secondary electrons produce topographic information about the sample. Yet, when SEM is joined with an EDX detector, X-rays can also be used as a signal to produce chemical information. To understand how these X-rays are generated, it's important to consider that every atom has a unique number of electrons that reside in specific energy levels. Under normal conditions, these positions belong to certain shells which have different discrete energies. The way EDX analysis works is that the electron beam hits the inner shell of an atom, knocking off an electron from the shell while leaving a positively charged electron hole. When the electron is displaced, It attracts another electron from an outer shell to fill the vacancy. As the electron moves from the outer higher energy to the inner lower energy shell, this energy difference can be released in the form of an X-ray. The energy of this X-ray is unique to the specific element and transition. The X-rays emitted during the process are collected by a silicon drift detector, which measures the signal and interprets it using software. In essence, the chemical information can be visualized in several ways, including elemental mapping and line scans. In this way, X-rays can be used to identify each element that exists in a sample. Interestingly, EDX can be used for both quantitative and qualitative analysis, enabling users to identify both the type of elements that are present as well as the percentage of each element's concentration within the sample. And as with traditional SEM, the technique requires little to no sample preparation and is non-destructive, meaning that it doesn't damage the sample. Because of its many advantages, EDX analysis has become common practice across industries ranging from manufacturing or research to energy and resource management to consumer packaged goods. In fact, it's so practical that it's now an essential part of owning an SEM. Using an SEM to perform EDX analysis, researchers can improve production quality while saving valuable time, all using a very simple experiment. SEM provides detailed, high-resolution images of the sample by rastering a focused electron beam across the surface and detecting secondary or backscattered electron signal. An energy dispersive X-ray analyzer is also used to provide elemental information and quantitative compositional information. SEM provides images with magnifications up to 50,000, allowing sub-micron scale features to be seen, in essence well beyond the range of optical microscopes. Rapid, high-resolution imaging with identification of elements present. Next is spatially resolved quantitative EDX analysis of user-defined areas on sample surface. Characterization of particulates and defects. Next is examination of grain structure and segregation effects. And coating thickness measurement using cross-sectional imaging of polished sections. Then application of EDX, characterization of material structures, assessment of reaction interfaces, service environment and degradation mechanisms, characterization of surface defects, stains and residues on metals, glasses, ceramics and polymers, measurement of the thickness of layered structures, metallized layers, oxide films, composite materials using cross-sectional imaging. And last is particulate and contaminant analysis on and within materials. So these are the spectroscopic methods. Thank you very much.